Why is the sky dark at night? Hardly the most profound question we face this week, but today is the day of the big questions. Some of them we know the answers to, and some we don't, at least not yet. Maybe it's your generation that's going to find the answers to the questions we're going to pose today. But let's start with one that we do know the answer to. Why is the sky dark at night? Now, I'm a theoretical physicist, and we theorists are renowned for being able to prove anything you like, even that black is white. So I'm now going to prove to you that the sky shouldn't be dark at night. Let me show you what I mean. Here's your eye looking out into the night sky. What do you see? You see stars. Just imagine a few stars fairly nearby, maybe 10,000 light years away. You just see them shining at you. Now, much further away, 100,000 light years, more stars. Each one faint because it's so much further, but there's many more of them that distance away. Go out further still, maybe 1,000,000 light years, fainter still, but even more of them. In whichever direction you look, eventually you find a star. You can see it here, filling in the gaps all the way across the sky. So wherever you look, there should be a point of light right the way across a white sky at night. Don't believe me yet? Let's do a real demonstration and show you. Imagine that this is the universe, and the camera here is your eye. It's going to look out across that universe at night for you. Let's see what you see. Now, we've got stars right the way across. We couldn't bring them all into the theatre, so I've brought them in some slices, 4 slices across the night sky. Let's turn on some stars nearby. What do you see? You see some stars twinkling. Now let's go further out and see what happens when we turn more stars on. It begins to fill in the gaps. And further away, and yet further away, until eventually the whole of the night sky is filled in with light. Wherever you look, there's light shining at you. The white night sky. So, why is the sky dark at night? Not such a dumb question after all. Well, this one we know the answer to, and it all goes back to the discovery of this man, Edwin Hubble. An American astronomer made one of the greatest discoveries of all time. In fact, so famous that they named a telescope after him. The Hubble telescope, which they shot up in a rocket and is now orbiting around above our heads, looking out into the night sky. This shows how important he is, because when the telescope wasn't working properly, they were even prepared to send astronauts up there to fix it. Named after this man. His discovery is perhaps one of the greatest discoveries in science, because it places us in the universe more precisely than anybody else has ever done. He discovered that the universe is expanding. Now, how did he do that? Well, let me give you some demonstrations to give you a feeling for how you discover the expanding universe. Let me begin with something that's familiar to you, sound. The reason I'm going to use sound is because in many ways it's like light. So, can we turn on the sound? Hear it as it goes round, up and down, up and down. Thank you. Whoa. Now, sound is like light. As it was whirling towards you, you heard the pitch go up. Away from you, the pitch dropped. It's the thing you're familiar with. Every time an ambulance or a police car goes past, you hear it. It's called the Doppler shift. What's happening is that the sound is being crammed up. The waves are being crammed up as they shoot towards you. The pitch rises. Going away, the pitch falls. Now, the pitch of sound is very similar, for our purposes, to the pitch of light. The pitch of light meaning the colour. Let me demonstrate what happens with real light, with a rainbow here in the theatre. So if we lower the lights, this rainbow will become clear to our eyes. There's a whole electromagnetic spectrum out there beaming at us, but our eyes only pick up that little rainbow in the middle, the colours of red through violet. You see it spread here before you. Now, different elements shine in different parts of the colours. Sodium, for example, shines in the yellow, and the sodium street lights shining yellow, very familiar to you all. Now, if that sodium light was on a star that was rushing away from us, its pitch would drop, just like the pitch of the sound. The pitch dropping means its colour would go towards the red. And if that star was going really fast, the pitch would drop far to the red. In fact, it would eventually go so far that it would be out the region that you could see. So it would be red-shifted so much your eyes wouldn't see it anymore. It would be like blackness out there. So what we have seen here, are you beginning to get the idea? Things rushing away, things go so far to the red, they eventually disappear. Right, let's look at our picture again. This is where we came in. The eye over here looking out into the stars. The nearby stars are shining at us. The further and further you go away, the stars get redder and redder until eventually it's shifted out of what you can see. Blackness. So the expanding universe, the pitch of the light changing, eventually you're left with blackness. There's a limit to the visible universe that you see with your eyes. And that all came from the discovery of Edwin Hubble 60 or 70 years ago. Well, that's half of what he did. The second part of what he did is even more interesting. Let's look at the next picture. It's not just that the stars are rushing away and making things red, but the further away you look, the faster they're receding. It's just like these cars here. Suppose that we're the observers here, the astronomers looking out into the night sky, and here is a galaxy fairly near, rushing away from us at, say, 30 miles an hour. And then, even more distant, is another galaxy that's rushing away from this one at 30 miles an hour, which makes it 60 miles an hour rushing away from us, faster. And an even further one is 30 from this and 30 from this, makes it 90 from us. So the further away they are, the faster they're hurtling away, the redder the light is shifted, until eventually it drops off into blackness. So there you have the idea of the expanding universe. Things rushing away from us, shifting into the red, until you can no longer see them at all. So this is the sort of picture that we have from Hubble's work. And I can show it to you now in a model of the real expanding universe. I said to Bryson Gore before we started this series, what sort of models can you make? Anything, he said. What about the Big Bang? Well, let's have the universe here in the theatre and see it expanding before our very eyes. Here is the universe. And on it, we can see some galaxies. Now, this universe is expanding. Let's make the expansion turn on. Here it goes. As it expands, the galaxies are moving apart from each other. And the further apart they are, the faster they're moving. Doesn't matter which one you're on, they're all moving relative to each other. Now let's stop the film a minute and just think. If the universe is expanding as we watch it now, imagine playing the film backwards going into the past. In the past, it must have been smaller than it is now. The film in reverse will be contracting. The galaxies must have been much nearer in the past than they are now. eventually all of the matter in the universe that we see today would have been crammed together very tightly on top of each other. In fact, it's that moment of expansion out from this original compact universe that we today call the Big Bang. Thank you. So, what have we learnt already? The universe is expanding, and from the measurement of the red shifts by Hubble, we know how fast it's expanding. Knowing how fast it's expanding, we can play it back. We know how long it has been since it was all crammed in on itself. So we've discovered the age of the universe. And the age turns out to be around 15,000 million years. So from those measurements, we've established one part of our story, the age that has been sitting on the top of these pictures here all the time. We know it by measurement, by Hubble's work. An amazing discovery. Because all cultures have been interested in this question of how did things begin, where did it all come from? We're no different. But we have put a number on it by measurement, 15,000 million years. Now that's one half of what we've done. The second thing that we've done, we've been able to measure the temperature of the Big Bang. We know how hot it was at the start. Now, how on earth do we do that, if that's the right way to say it? You can't go back to the Big Bang and put a thermometer in it and see how hot. Well, let me show how we do that. That all begins with the story from these two gentlemen. Now, this isn't a police mugshot. This is actually a picture of two famous astronomers named Penzias and Wilson. They were working in New Jersey in America about 40 years ago, and they had this rather odd-shaped telescope. It's called a microwave telescope. They were looking out in the sky, looking for objects that radiate at us in the microwave part of the spectrum. And they had a problem. It didn't matter which way they looked, there always seemed to be this sort of hiss in their telescope. They couldn't get rid of it. What on earth was causing it? Well, they looked inside the telescope, couldn't find anything wrong. No obvious signals of noise in the laboratory causing it. They even thought that pigeon droppings might be causing it. They cleaned the telescope, still the hiss, whichever way they looked. Eventually they realized what it was. This was coming at them from the universe. They had detected the radiation, heat from the Big Bang today. What's more, they measured its temperature. But let's go along with this and see where it leads us. We can turn the signal from their telescope into sound electronically, so we'll be able to hear the Big Bang. Now, so that you're sort of ready for cueing what it's going to sound like, what I'm going to do first of all is to play you a tape not of the Big Bang, but of an earthquake. So you'll hear the sound of an earthquake having been processed electronically. You'll hear the thing go boom, 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 boom as it hits the surface of the earth and bounces back. And after that, when you've got used to that, we will then hear the sound of the radiation from the Big Bang. So let's hear the earthquake. So that's an earthquake. Now let's hear the remnants of the heat from the Big Bang heard by Penzias and Wilson. Just uniform. Whichever way you look, it's just the same everywhere. In fact, very precise measurements, even in this last year, have shown that the deviation from that uniform hiss is at about 1 part in 10,000 at most. And that is the sound of the Big Bang, still echoing around the universe 15,000 million years later. You can even pick it up on your own television. At night, after all of the decent programs have turned off, you're left with noise on the TV. You just can't get rid of it. Now, most of that noise is just electronic noise from your electrical circuits in the house or things going on around the town and so forth. It's always there. Now, imagine that you could clean it up and get rid of all that earth-based noise. You would still be left with a little bit, about that much of the lot. Now, that's not Sky TV, but it is television from the sky. about that amount of your noise on the television set is coming from that background hiss from the Big Bang. So you can hear the Big Bang, and you can even pick it up indirectly through your television set. Now, to pick it up really clearly, you have to have a modified television set, and that is indeed what Penzias and Wilson were using, a microwave aerial specially tuned to listen to that part of the spectrum. And that's how they picked the whole thing up. And the most important thing of all for us is that they were able to measure its temperature, just 3 degrees above zero. And that's the second key we need, because I'm now going to show you what that means. Let's think what we've got. We know the universe is expanding, so in the past it was much smaller, much more compact. Let's see what happens when things that are compressed, like the early universe, suddenly expand out. Watch this. So Bryson down here has prepared for me a model of the universe, very compact under the table, and I'm now going to release the pressure and see what happens. Snow. It gets cold. Let's do that again. Wow. I knew Bryson could make the Big Bang, but I didn't know so successfully. So what you've seen there is a demonstration. When you've got things that are really tightly compressed and the compression is released and they expand out, they get cold. Now think about that for the whole universe. Originally highly compressed and shooting out and getting cold. And Penzias and Wilson have told us how cold it is now, 3 degrees above zero. So we know the temperature now, we know how old it is, we know how fast it's been expanding back to the Big Bang. We can work it all out and get the temperature at each and every stage throughout history. Who's going to help me complete the picture behind us and put the numbers on? Would you like to come down? You're obviously prepared. You've got your gloves on. Right. Your name is? Olivia. Right, let's come around the back here and we'll put some numbers on. We're going to need some spray paint. That's why you've got gloves. They didn't provide me with gloves. The budget must have run out, so I'll keep out of your way. Right, let's come over this side here first of all. So here we are, 15,000 million years after the Big Bang, and Penzias and Wilson have told us the temperature is this. So would you like to spray the numbers on? Okay, very careful. 3 degrees, very clear. Okay, let's move back to another important signpost in the universe, 300,000 years afterwards, and we'll spray the temperature on there. Okay? Okay? 3,000 degrees. That's about half of the temperature of the visible surface of the sun. Just cool enough now that atoms can hold together. Let's go back right to the beginning, to the very hot part, just after the first particles of matter were being created. Let's spray this on. Down the bottom. Okay, that's it. Million billion degrees, the temperature just after the Big Bang. Thanks very much. So, what we've achieved is we're beginning to complete the picture. We know the age of the universe, we know its temperature at different times, and it's from that and our knowledge of physics we've been able to work out what happens at each and every stage from the beginning up to now, with a few bits still remaining to be filled in. So, we know back at the start of time the temperature was like this. Now, can we go and see that? How can we look at it? Well, the way that we do it is to make huge particle accelerators and speed the particles up and smash them into each other. Because smashing them into each other recreates momentarily conditions of extremely high temperature. And once we get to this sort of temperature in those collisions, we are seeing the physics of those first moments. And we do that at various laboratories around the world, such as at Geneva. And what do we find? We find that this energy produces matter and antimatter in equal amounts all the time. Now, that's a puzzle. And it's one of the big questions we're going to have to face. Energy turns into matter and antimatter under these conditions. The universe cools, and what are we left with today? Well, the energy is still around. That's what Penzias and Wilson discovered for us, the 3 degrees cold remnant of that original energy. The matter is still around. That's us. What happened to the antimatter? It's all disappeared. Well, our conjecture is that just after the matter and antimatter were created, the universe was so compact they bumped into each other again and annihilated. Let's see if we can replay that in the theatre to get an idea of what's going on. So, Bryson has created some more magic for us. Imagine that this is a snapshot of the universe just after the matter and antimatter has been created in that first moment. And the matter and the antimatter are the purple and the white bits, created in equal amounts. And then they bump together again and annihilate. Let's see what happens with annihilation. Well, what are we left with? You think that's a mistake, don't you? That's you and me and everything. Somehow, the antimatter is gone and a little bit of matter has been left over. That little bit of leftover matter are the stars in the sky and everything around here that you can see. So the matter of the universe that we know today is just a little bit that got left over from the Big Bang. The flash that you saw has cooled off with the universe and is the 3 degrees background radiation that Penzias and Wilson have seen. But that is us. Interesting. Thank you. So, the matter that's left over is us. Let's see what we know about that matter. Begin to make sense of the leftover bits. Well, here we've got some models of the atomic elements. The light ones, the simplest ones, hydrogen and helium, are simple because their nucleus is itself very simple. Hydrogen just contains a single positively charged proton in the middle, made in the first moments of the Big Bang. Helium is also fairly simple. It's got 4 members in it, and that also gets formed a little bit later after the Big Bang. That we can all understand. But what is the puzzle is, look at these other elements like carbon and sulfur. They're getting bigger and bigger nuclei, more and more complicated. And the very heavy ones like iron and copper and so forth have really big nuclei. How on earth did these things get made? Well, that's the question. What we think happened is the following thing. And I'm going to show you on a video. We're going to take a journey together from the Big Bang. We're going to hitchhike a ride on one of the first particles to be made, a proton. So, here's the Big Bang happening, energy bursting out, and after about 1/1000th of a second, the primeval seeds, the quarks, will appear, and here they are, gradually forming themselves in groups of 3s to make the thing we call the proton, eventually the seed of hydrogen. So here, the first protons are forming, and they're just hurling around, and eventually here's the one at the bottom that we're going to take our ride on. So let's sit with this and watch what happens. There's lots of protons. There's nothing other than protons, all of them hurling out from the Big Bang along with us. But gradually, you see, as it cools a bit, they start clustering together, little groups of 3s and 4s. Helium is also being formed. Very quickly, there's so much of this around that gravity starts pulling it together, and you begin to get these huge masses of hydrogen gas that we call galaxies of stars. And here we're beginning to zoom in towards one of those stars, because our proton, the one we're sitting on, has been trapped by the gravity of that star. There's the hydrogen atom shooting in to one of these hot stars in the early universe. And here start coming in other protons. Everything is tumbling in to that star. As they do so, getting hotter and hotter, providing the fuel to keep that star burning. And as we look in the middle of the star, now see what starts happening. That the simple nuclei start bumping into each other and building up more complicated nuclei, the seeds of the heavier elements, getting as complicated as carbon and going up bigger and bigger. Eventually, getting a huge cluster together, a nucleus of iron. Now, the star can't hold together much longer, and eventually it explodes and throws this iron nucleus and all the other heavy nuclei out into space, polluting the cosmos. And it's that, we believe, happened about 5,000 billion years ago at the time when our solar system was forming, and those heavy elements from a long-lost star polluted all around here and ended up as the carbon that's in your bodies and the oxygen and everything else around us here today. So that's the sequence that we believe happened. No, it's not just belief. In fact, this is still going on, and we have seen it going on very dramatically just 6 years ago. One of these explosions, they're called a supernova, happened in the southern heavens. Here is a picture of the Large Magellanic Cloud. It's a small galaxy just off the edge of the Milky Way. You can't see it from up here because the Earth's in the way, but if you go down to Australia, you can see it in the heavens. And in 1987, suddenly, in the middle of this galaxy, a new star erupted, called a supernova. Now, in fact, it really happened 200,000 years ago, because light takes that long to get from there to here. What's happened recently is the astronomers have looked at that supernova again and see what they find. There is the star that's exploded, but look at this ring all the way around the outside. That is debris that has been thrown off, heavy elements in there being thrown out across space, just like happened 5,000 million years ago around here. So maybe that already is beginning to see new life forms that will be developed from these heavy atoms from that supernova. So what you're seeing here is the actual explosion of a star, and the astronomers have been studying that over the last 6 years and learning what actually happens when stars explode. And the amazing thing is that what happens seems to fit in exactly with what we think should happen, with our theories of how the elements are born. So, this seems to be the explanation of the matter that we know and love, that makes us. The very simple bits formed in the Big Bang, ended up in stars, built up the heavier and heavier versions, the star exploded, polluted the cosmos, ended up in us. So we seem to have a pretty good picture of matter, and there it is. So, we've explained matter. We've explained the universe out there. Well, not quite. We've explained between about 1 and 10% of it. There's a little bit, the majority of it, is some mysterious stuff called dark matter. Now, this is very odd. There's stars or stuff out there that we cannot see, yet we know that it's there. Now, how on earth do we know that? Let me show you a picture. This is a picture of a spiral galaxy. It's just like a Catherine wheel going around on firework nights. You can get the feeling of the thing whirling around like this. It's not just the feeling of it whirling around, it actually is. How do we know that? Well, we go and look at the light being emitted from the stars. Remember when we were whirling around and you heard the pitch going up and down as it came towards you and went away from you? Same thing with this. You look at the light from the stars on the edge of this spiral galaxy and you find some have been shifted towards the blue, as if they're coming towards you, and some have gone to the red as they go away. So from this you get the feeling that this whole galaxy is swirling around, and you can measure the speed that it's swirling around. We can also weigh it. And what we find is that when you weigh the galaxy and compare it with the speed it's whirling around, the sums don't add up. Let me show you what I mean. I asked Bryson to make a galaxy for us, and he's obliged. And this is what happens with a spiral galaxy. The thing is rotating around, and there's some stars sitting there quite happily. But what's supposed to happen, according to our sums, is the following thing. If our sums are right, the stars should just fly off because it's going around so fast. Yet they don't. Let's just look at this picture again. So, we see these stars whirling around and staying in the galaxy. Yet, when we look at all the matter in the middle, the amount of gravitational tug that it can provide to hold them on the trail isn't enough. Those stars have no right to stay there. They should just fly off the wheel, like in Bryson's demonstration. How do they stay in place? There must be a much bigger tug going on to hold them there, provided by stars that we can't see, dark matter. Now, it's not just this one galaxy that's got this problem. There are many, many like this, and not just individual galaxies. We see galaxies and galaxies rotating around each other, and we begin to find that the sums don't quite balance. It really does look as if there's this dark matter in the universe, maybe 90% of it. Now, how on earth do we go and look for dark matter? Well, one way is by analogy with H.G. Wells' story about the invisible man. You didn't see him directly, but when he bumped into things, you were aware of his presence indirectly. That's the sort of thing we're doing here. Now, what is really exciting is that as I was preparing these lectures, the first news came out that perhaps the first sightings of dark matter had been made. And this is shown in these pictures that were published just a month or two ago. Some astronomers were looking at some stars, and it's been processed through the computer. You see these little pixels to show the stars. I want you to focus on this star in the middle, and we're going to play in a moment. We'll show what happened over a period of weeks. So this was at the beginning of a period of time. Now, a few weeks later, this had happened. Suddenly, it was brighter in the middle, and then a bit later still, it had dimmed away again. So there you are on Earth, looking out at a star in the distant heavens, and suddenly it gets brighter and goes away. Now, what's going on? The idea is that a dark star has come between you and it. Sounds very odd. Let's just look at this again fast to convince ourselves that it is brightening and going away again. So, that's what was seen. How on earth can it be that a dark star has come between your eyes and that distant star and made it brighter? You would think that it would block it out. No. Another of Bryson's amazing replications of the universe here will show us how this really works. Now, this might look to you like just a sheet of latex rubber, but in actual fact, this is the universe. And at this end, we have got the astronomer who is going to be looking out at a distant star. And at this end, we have the star. Now, can I have a volunteer to send me some light beams from the star? Would you like to have a go? Right, what's your name? Paul. Hello, Paul. Now, could you just roll a couple of balls from here? First of all, just roll one straight so we can get the idea across the flat plane. So you see, this would just come straight in to the telescope waiting to receive it. Now let's see what happens when I put a dark star in the middle. Okay, fire one straight at it again, see what happens. It hits, you see. You don't see that one. But let's see what happens to a light beam that goes slightly to the side. You want to move that slightly to the side, that's right. Now let's see what happens with this. You pick it up, you detect it. It's got bent. Let's try with a light beam on the other side. Okay, fire us a light beam. That also got bent. So suddenly you're seeing more than you would have done before. Thanks very much. So what has happened is that the dark star has bent space, and that will bend light beams around it. It's like a gravitational lens. It's really acting like a lens. Let's see lensing and demonstrate this again. So over here, we've got the Earth, where your astronomer, you, are looking out into the night sky. And over here, we've got a star, which Bryson is now going to switch on, and you're sitting on the Earth watching it. Now here, we've got a dark star, which is going to come between you on the Earth and the star over here. Now you watch the Earth and see what happens as the dark star gets in the way. The dark star comes across, and when it's right in the way, the Earth is brighter. The star is shining brighter, and then the dark star goes and it dims again. Let's see that again. So it starts off, you're looking at the star, it's fairly faint. When the dark star gets right in the way, the distant star gets brighter and then goes dark again. So you see the lensing effect, exactly the same as that sequence of pictures that we saw as it went brighter and then darker again. So, dark matter has been found. Let me show you this more graphically, what we've just been demonstrating. Here is your eye on Earth. Here is the distant star that you're looking at, and here is the dark star, at present not yet in the way, and a light beam is coming at you. That was just like the single ball that rolled across the flat latex universe. Then the dark star got in the way. What happened? A direct hit doesn't reach you because the star's obstructed it. But this lensing effect bends rays that would have missed back into your eye on both sides. So you get this surprising result that when this gravitational lens, the dark star, is directly in line, you get more light at your eyes than you would have done. The thing brightens, just like that sequence of pictures that were discovered a month ago. So that is the first discovery of dark matter, of dark stars. The question now is, what is this dark matter? Is it ordinary stuff like you and me that just is out there and not shining? Or is it exotic stuff? Stuff that we don't know of around here? Well, this is a big discussion that's going on at the moment. Many people think that it might be made of mysterious stuff called superparticles. Now, that would be a whole series of lectures in itself, so we're not going to follow that route. But, listen for it. You might hear words like superparticles and supersymmetry being bandied around in the next few years. Maybe that's what it's all about. We don't yet know. So, let's really reflect on where we have come. We've discovered that our place in the universe has got less and less significant. Hundreds of years ago, we thought that we were the centre of the universe. Then it was discovered that we weren't. We were going around the sun. Now, that discovery itself sent people to prison because it was so heretical. Now we know not even the sun is the centre of the universe. The sun is orbiting around the galaxy, and the galaxy is orbiting around the universe. In fact, we're getting less and less at the centre of the universe. And now it's even possible that if that dark matter is made of exotic stuff, and that's 90% of the whole show, that we are made of pretty sort of small stuff, that we are like flotsam on a sea of dark matter, only very minor players in the whole show. So our position is getting less and less significant. Very bizarre, very surprising. That's the way it is. I'm now really beginning to get to the final phase of all this, beginning to face these questions. And the big questions seem to be, one, how did all the antimatter go, and how did there be an excess of matter left out of it all? Secondly, how did it come about that we started with this uniformity in the Big Bang and ended up with galaxies of stars randomly distributed around the sky? And the third real question is, and how did all this mass come about anyway? I mean, according to all our theories and equations, when the universe began, everything would be flitting around at the speed of light with no mass at all. Now, these are three big questions that we're trying to get to grips with. And surprisingly as it might sound, there appears to be a common thread to them. And now I want to sort of move towards these frontiers that currently are beginning to attract our attention and see where they lead. So, the common thread seems to be this. We started off with a hot Big Bang where everything was uniform, very high energy. And now we have ended up with a cold universe, highly structured and lopsided. How did it come about? You went from this uniformity to this lopsidedness. What triggered that thing? Well, it turns out that this change from uniformity to lopsidedness is much more common than you might realize. We've got some demonstrations of the disappearance of symmetry and the appearance of asymmetry, as it's called, here in the room. Now, the first thing I need is a volunteer who is highly symmetrical. Are you a highly symmetrical volunteer? Yes, okay. What's your name? Catherine. What I want you to do is to stand on that cross, which has been prepared very accurately, and be as symmetrical as you can, and Bryson is going to bring on the apparatus. Right, so you are positioned symmetrically exactly halfway between two identical bars of chocolate. Now, what I want you to do when I say go, you can choose either one of those and pick it up. Okay? Great, well done. I think you did so well, you can keep that. Thank you very much. Look what we've got. We started off with this completely symmetrical beginning, and then by some random choice, asymmetry. So that's a simple example of asymmetry out of symmetry. Now let's take a second example of going from a high energy state to a low energy state and seeing how the universe might change. So this is the next of our demonstration, and for this I've got 3 of our volunteers here. In fact, these are 3 of the ladies who have been helping Bryson and his team make many of these demonstrations, so if this one doesn't work, it's their fault. Right, okay, Zoe. What we've got down here is an empty drink can, which Zoe is going to stand on and balance, and Karen and Jessica are just going to help support her balance, okay? So we see the drink can supports her whole weight. Righty-ho, get the whole of your weight on there, and I will introduce a bit of asymmetry. There we go. Thanks very much. So we started off with that very highly ordered drink can, just like the highly ordered early universe. A little bit of asymmetry was introduced, and now you're left with this. This is the universe today. There's no way you would reconstruct the original drink can out of this. Something made the change. So that is the sort of idea we have. Let me give you an example from the real universe. Here, I'm taking a drink of a well-known substance, water. Nice and warm. The molecules in it whizzing around in all directions, complete uniformity and symmetry. Freeze it. You have the snowflake. Beautiful structure, highly ordered, but no longer the total uniformity. A clear, structured system. You've gone from the liquid state, where it's warm, high energy, to the frozen state, and you've got structure. That is the sort of idea we think is going on in the early universe. So, what we've done, we've gone from hot, like the drinking water, to the frozen cold, like the present universe with structure. The question is, what introduced that asymmetry? What triggered that change of phase, as we call it, from the liquid to the frozen structure that we see today? Now, there's many ideas about, and this is really one of the hot topics at the moment. And among the front runners is an idea due to this gentleman, Peter Higgs. Now, Peter Higgs is Professor of Theoretical Physics at Edinburgh University, and his theory is the one that is currently the front runner and that everybody is trying to get to grips with. And to summarise it in 4 lines, there it is. I don't need to say any more. Well, yes, I do. I mean, I must stress here that now we're really at the cutting edge of science. We're getting to the point where we are trying to understand these ideas, which are really only yet being formed. But let me see what we can do. Here we have got a model of the universe. At the start of time, we've got two identical particles. Now, when the symmetry broke, it could have gone the red way or the blue way. Some, we don't know why, but some particles feel the red route and just go happily straight down, sort of flighty, fast, moving like the speed of light. Other particles, however, feel they get gripped, they get slowed down. There's an inertia about them. They sort of get weighty and heavy. They've gained a mass. Let's sort of show this again. Some things don't seem to care, and other things get gripped by some force, the Higgs force, a fifth force in nature. Now, this idea of a fifth force in nature is something quite new. In fact, even in my own books, I say four: gravity, electromagnetic, the weak and the strong. Now, if Higgs is right, there's a fifth force about, and it was this that triggered this change. Now, this is so exciting, people, that almost all the theoretical particle physicists in the world are currently trying to understand this, devise tests of it, and do experiments to see if it's right. And it's been so interesting to people that even our science minister, Mr. Waldegrave, decided that he would like to know much more about it. And he issued a challenge earlier this year to the scientists to say, could we describe to him the idea of this Higgs force on a single sheet of paper? And he offered the prizes of bottles of champagne for the best solutions. Now, I was one of the many entries, and I was a little bit worried about this because there's this famous case that Richard Feynman, a well-known physicist from the past, just after winning his Nobel Prize, was asked by an enthusiastic reporter, could he describe his Nobel Prize in 30 seconds? And he said, if I could describe my Nobel Prize in 30 seconds, it wouldn't have been worth the Nobel Prize. So I was a little bit worried about the idea of being asked to describe these very complicated ideas on a single sheet of paper. But I said, I'll be happy to try to do that if in return you will do the same on behalf of the Maastricht Treaty. I didn't win. But one of the winners was Professor David Miller from University College in London, and he obviously had his eye to the main chance because he came up with a very nice political analogy which you've had transferred into a cartoon sequence to explain it. So his idea was, imagine the universe filled with party political workers from the Blue Party, and here they are. And see what happens when a particle comes into the room. So here's a particle entering the room. And immediately, all the Blue Party workers rush over and gather around her. This is the Higgs force at work. They're clustering around this particle as she enters. The result of this is that she sort of gains inertia. It's hard to move. But once moving, it's harder to stop. And so here you have the idea that this Higgs force grips itself onto certain types of particles, the ones that go the blue route, and give them this inertia, a mass. And that is at the root of the mass of particles, this fifth force, the Higgs force. Now, if this idea is right, we're going to have to look for some ways of testing it. And this is now what people are about to do. Now, Bryson has made a demonstration here, and it goes back to the days of Faraday, who founded these lectures 160 or so years ago. Faraday was famous, among many things, for discovering the secrets of electricity and magnetism. And this is a demonstration of magnetic effects. So think magnetic forces for this demonstration at the moment. And you see, as Bryson moves the magnet around underneath this, these iron filings are sort of representing the field of the magnetic forces. The magnetic forces cluster the iron filings into clumps. Now, these clumps show up in our detectors like particles. Now, instead of thinking this real thing as the world of magnets and magnetic force, think of it in the world of Higgs force. This is the field of blue party workers clustering around. And the clusters in this field of the Higgs force will manifest themselves as particles. The basic idea that we have today is that forces are transmitted by particles, and this Higgs force will be transmitted by Higgs particles. These force carriers, we call them bosons. So this is the Higgs bosons that everybody's looking for. If this idea is right, they are the things that we will find first. Well, the hunt for those things is on right now. This is actual living science of today. And what the answer is going to be, I don't know. That's for the future, for another year. So let's bring this whole series now to a close by asking the question, why do we do it anyway? Well, one answer to this is that it's answering the big questions of how did it all begin? How does the universe work? What's it all about? And that is a great cultural drive. It's been common to cultures throughout history. And we're the first to have been able to put numbers on by experiment. So we are lucky to be alive at a time when these sort of questions are being answered. The second thing that comes out of this is that you suddenly discover things that you didn't expect. And you open up totally new avenues that nobody knew was there before. And let's stick with the case of Faraday and draw the analogy with Faraday again. Back in the 19th century, Faraday was doing experiments just by curiosity. He was interested in electric and magnetic forces. Faraday discovered that electricity and magnetism were not two different forces, but one, which we now call electromagnetism. He discovered that when he sent an electric current down a wire, and that there's mercury at the bottom of the tray that conducts it, electricity and magnetism conspire to make motion. You've got the original motor. So that discovery came just from curiosity. And today you have lights and television and the whole of modern electronics and communications going back to those curiosity-driven experiments of Faraday here at the Royal Institution. So that shows that you can end up with things you never anticipated to begin with. Now, Faraday tried doing much more than that. I mean, in his day, the only forces that were known were gravity, electricity, and magnetism. Having successfully united electricity and magnetism into one, which we now call the electromagnetic force, gravity, he tried to bring into the picture. And here at the Royal Institution is a cartoon showing an experiment that he did, trying to unify gravity and the electromagnetic force. He dropped some spheres from the roof of the RI down onto a cushion at the bottom, past an electric coil, hoping that an electric current would pass and be revealed on this counter. He didn't succeed. And we haven't yet succeeded today. But this is another of the big challenges that we're trying to face. When we look at the equations, we get the feeling that deep down, gravity and all the other forces somehow are the same. And maybe Faraday's idea of trying to unify them was the right thing to do. But now we know so much more that maybe we'll be a little bit nearer to getting there. And if it succeeds, who knows where that goes? So let's think about Higgs and go out with this. If the Higgs force, the fifth force, really is the source of the mass in the universe, what might that do? Let's, for the last time, look at the most famous equation in physics. E equals mc squared. Mass is energy. And the relationship between them is this huge number, the velocity of light squared. What this is saying is that mass contains energy. Mass is energy. You can get energy out from mass. That is what may be the exciting future. You see, what I've got here is a little 1 kilogram block. Imagine that this was a 1 kilogram block of chocolate. If you eat this chocolate, it will provide you yourself with enough energy to keep going for about a day. The most efficient energy process that we know has still only been able to extract at most 1% of the total energy contained in the E equals mc squared. Just imagine what we could do if we could get all of it out. There's enough energy in the mc squared of this block that if you could extract it and use it, it could supply the total energy needs of the whole of the country for a week. Now, I don't know if it's possible to do that. But if it is possible, then I feel that if we really understand what mass is, then maybe that might be the key to getting it out and doing it. That's for the future. So that is the big question that we're pursuing right now. We're building a huge machine in the hope of being able to solve this question of what's really going on. What is the source of mass? Is there the Higgs force out there? These are the exciting questions that we're looking at, and the answers will probably be coming sometime in the next 10 to 15 years. Now, there's many of you in this room here who are of an age that in 10 to 15 years' time, you could well be doing your PhDs, probably in particle physics. And just imagine for a moment, it could be you doing the night shift, looking at the computer, all on your own, 3 o'clock some morning, early in the next century, when the picture comes up before you, and there it is. Suddenly, the proof is there, and you are the first person in history to know this secret of nature. All the generations that have ever lived do not know this fact. There are 5 billion people on the planet who do not know the fact that you there are looking at a new secret of the universe. From tomorrow, everybody will know about it in the papers and the media, but for this moment, it's your discovery. Good luck.